the logarithmic energy on the sphere and the astounding connections to it. So without further ado, Ujué, please, the screen is yours.
Okay, thank you. Thank you very much, Samir. And I also want to thank the other organizers. So yeah, Ryan and Alex, thank you very much for wasting this time. It's not waste time, never mind, on organizing such a nice seminar, right? Before the talk starts, I'd like to give you a couple of ideas or how this is going to develop. So first thing, I prepared the talk for an audience based on mainly PhD students and graduate students. I see many senior researchers here, so I'm sorry if that's too basic for you, but that was the main public. And secondly, I'm here not to present a single result and a detailed proof of it, but rather than that, to give an overview of a lot of different problems that had to do with this problem of minimizing the logarithmic energy. So my aim today is to show you different fields of mathematics that are connected to these problems, to show you what I consider the principal results of every field, and to show you what is the limit and where the results stop and the open problems begin. Right. So saying that, let's start. And let's start with this notion that is the main notion during this talk, that is the logarithmic energy. Okay, so we are going to work with a set of endpoints on the sphere of dimension 2. And we are going to call this set always omega n, when n is the number of points that we are taking. Also, we are going to denote by x sub j the points on the sphere. So given that, the logarithmic energy of a set of points, omega n, is just the sum of the logarithm of the inverse of the distance between every pair of different points. That's the main definition. Of course, you know the properties of the logarithm, so we can take out here a minus sign, and then we have the logarithm of the distance of the points. We can think a little bit about this quantity to get with some intuition about how is it behaving with different set of points. Let's think, for example, that we have twice the same point included here on the set. So let's think that x1 equals x2. Then, if we compute the logarithmic energy, here we have a 0, right? So, sorry, here we have a 0. So we have the logarithm of 0. We have something that is going to infinity with the minus sign. And in general, if we have 2 points that are really close on the sphere, then the distance between there is going to be small, and the logarithm is going to be really big. Right? So we are going to have kind of little explosions if we take points that are close. Instead, if we take points that are nicely distributed, meaning that we have some neighborhood surrounding every point in which no other point is contained, then we will be able to manage this quantity. This can be somehow bound. All right, so I told you this is the main, the main thing we are working with today, but why? Why are we using this logarithmic energy? I should be able to go to the following, yes. Okay, I can give you 2 ideas. Why are we studying, or where does this logarithmic energy come from? And you can think of it as a limit case of the Riesz energy. So you know the Riesz potentials, or Riesz energy, are a family of potentials defined by this expression here. So we have a parameter s, and then we define the Riesz energy of omega n, a set of points on the sphere, by the sum of 1 over the distance in between every different pair of points up to this power s. This is a large family of potentials, and maybe the better known potential among the Riesz family, Riesz energy family, is the Coulomb potential that is obtained just by taking s equal 1 here. Okay, So we have those Riesz potentials, and we can define them for any positive S. Not only positive, but for every positive S. And then we wonder what happened when S equals 0. And if we take here S equals 0, then this is always 1. And so this number is just a combinatorial number depending only on the number of points that we have, and not depending on the distribution of the points on the sphere. If we fix n, then this is always the same quantity. So it's not really an interesting quantity because it's not telling anything about the distribution of the points in the sphere. So S equals 0 is not an interesting quantity, but we can see what happens when S goes to 0. And if we compute the derivative of such a thing, and we take it when S equals 0, what we obtain is exactly the logarithmic energy of the points. So this is an explanation of, a possible explanation of where does this logarithmic energy come from. We have this well-known family of potentials, and if we take the limit and the derivative when S equals 0, then we have the logarithmic energy of the points. This is one explanation, but I want to give you yet another one. And this comes from a physical problem, but of course, after some mathematicians working on it, rather a lot of mathematicians working on it, we lost all the physical aspect and we started with really abstract things. And the motivation is the following. Just take a sphere of dimension 2 and think that we want to place on the surface of the sphere some heaters, some radiators that are going to warm up the sphere. Right, then I can situate my heaters or my radiators on different places on the sphere. And I can wonder what is the average temperature on the sphere if I don't consider the point where the radiator is and a little neighborhood surrounding this point. Okay, then yeah, I can ask myself, what is the average temperature? And then I can ask myself the following problem. What if I want to have the maximal possible average temperature? Then where should I place my radiators, right? If I take all my radiators, let's think on the sphere up the Earth, as the Earth, and if I take all my radiators close to the North Pole, it's going to be really hot on the North Pole, but then on the rest of the sphere, it's going to be cooling down. Of course, this is a very short way of talking about it. We did some initial conditions, right? And how does the temperature spread out and everything. But that's the idea. Okay, and now we are mathematicians. We are not longer worrying about heaters or radiators. And we just want to place some points on the sphere that we consider as sources of heat. Okay, and we want to maximize the average temperature on the sphere, excluding the points, which are the sources, and some little radius, some little neighborhood of such points. Okay, then I can ask myself this question: where should I place the points so that the average temperature is maximized? And the answer to this question is, okay, you have to place the points exactly on the minimizers of the logarithmic energy, right? So if I want to maximize the average temperature, I should place my sources of heat on the minimizers of the logarithmic energy. We will then explain a little bit why, but mainly because this potential here is the green function of the sphere. All right, so we have two problems that are related to this minimization of the logarithmic energy problem. First one is to find the minimizers. If I tell you, hey, I have n points, if I have n equals 1,000, I have 1,000 points, and I want to place 1,000 points on the sphere so that they minimize this quantity here. That's a problem. And as long as I can ask you for 1,000 points, I can ask the same question for any n natural number of points, right? find the minimizers of the logarithmic energy. And another problem related to this is, what is actually the value of the logarithmic energy, of the minimal logarithmic energy? Of course, if I answer the first one, I can answer the second one. If I know where the minimizer should be placed, then I just have to compute this logarithm of the distance of the points, and I know the value for the minimal logarithmic energy. The other way around is not that easy. But I want to mention those are the principal problems regarding this minimization of the logarithmic energy. One, where should I place the points? Two, what's the value of this minimal logarithmic energy for any n? All right, there are two problems, two well-known problems related to this minimization of the logarithmic energy. The first one that I wrote down as a facility location problem is just this problem of the sources of heat on the sphere, and then we have the green function going down, blah, blah, blah. We are going to watch this later. But just in case I forget to mention about this, this is collected on this article of Beltran 2014, where he explains this physical problem with initial conditions of the maximal average temperature. And the second famous problem that talks about minimizing the logarithmic energy is known as a Smale's seventh problem. Steve Smale is a very famous mathematician that has worked in many, many different fields of mathematics. He is a Fields Medal winner. And for the year 2000, he wrote this list of 18 papers, 18 problems that he considered to be the important one to solve in this century. So he proposed 18 new problems. Of course, they are not new at all. Some of them are very famous, as the P versus NP or the Riemann hypothesis. And in between this massive list of problems, very difficult problems, we can find a problem, namely number 7, concerning this minimization of the logarithmic energy. So let's have a look at the explicit description of this problem. For that, I'd like to refer from now on as Mn to the minimal logarithmic energy for n points. So here I let omega n vary in between any set of n points on the sphere, and I take the minimal value that this energy arises. Okay, so this is going to be Mn, and Smale's seventh problem asks us to give a set of n points, and he's not asking for minimizers of the logarithmic energy, as I was doing in the previous slide. He's asking for points that are close enough to minimizers of the logarithmic energy. And this close enough is written down specifically in this way. The logarithmic energy of the set of points that the problem is asking for has to be close enough to the minimal logarithmic energy, at least to a log n, when n is the number of points, term. Right. This is, of course, a result with asymptotic flavor, right? Because here I worry, especially when the number of points goes to infinity. And this is where this log n is playing a role, an important role. Right. So not only minimizers, but points that are close enough to the minimizers are really important. And if they are close enough in this particular sense, the difference between their energy and the minimal possible logarithmic energy is bounded by some factor of log n, then we are done with Smale's seventh problem, which is nice. It's quite nice. Right, so we know some things about this minimal value of the logarithmic energy. And that's rather important, because otherwise, even if we have a really amazing set of points, we could not compare with the minimal value, right? So what do we know about this minimal value of the logarithmic energy? The first result is due to Fekete. Fekete has worked a lot on these problems, and this is why sometimes these minimizers of the logarithmic energy are called Fekete points, or elliptic Fekete points. And he proved in 1923 that if we take the sequence of minimal values of the logarithmic energy, the sequence is indexed on the number of points, and we divide it by n squared, n again the number of points, then this sequence here is upper bounded. And the bound that we found is this number here, 1/2 minus logarithm of 2. And this number here is not just a number we have found and that's all. That's, of course, the value of the, let's call it, continuous logarithmic energy. Meaning that if I integrate the logarithm of 1 over the distance in between 2 points, but then I don't take these 2 points on a finite set of points, but instead I take in on the sphere with the Lebesgue measure, then the value of this integral is exactly 1/2 minus log 2. To make everything clear, here I'm taking the Lebesgue measure, but normalized so that the measure of the sphere is 1. Right. So what does it mean? It means that we have a first term if we want to compute the asymptotic expansion of the minimal logarithmic energy. Because now we know that this Mn is this constant that we obtain here times n squared, the number of points squared, and then some little order terms. Right, so we are good. We have the first term. Of course, we know more. This result here, the second result, is not due to Elkis and Lang on a joint paper in '88, as it may seem for my writing here. This is a technique proposed by Elkis and then used by Lang in his book in 1988 that allow us to give lower bounds for some kind of energies. And using this technique, we can give, we don't have an equality, we have a lower bound for the minimal logarithmic energy, we can give this second term. So the first term, we know it since 23, and here we have the second term that is -1/2 n logarithm of n. And then we can even say, this is the following term, big O of n. All right, so this was known in 1988, and in the following year, Wagner, using another kind of arguments with the stereographic projection and some Hadamard inequality, was able to prove the following bound. It's essentially the same, but here we can forget about this big O of n, and we have a constant times n, right? And this was the current knowledge for a while. And then we have several works by Rachmaninoff, Safansu, Dubikas and Brauhart, Harding, and Saab, working on specific constants, specific values of this capital C. And that was everything until 2 years ago. Betterman and Sandier came with this beautiful result. And here we are losing the inequalities and we are going back to an equality. So they were able to prove that this minimal energy, logarithmic energy, is, we have the first term, the second term, and then they proved the third term was a constant times the number of points. And then some lower order terms. And that was really a big result that was, has been looking for since at least '88. And they came to it using some really nice mathematics, I should say. Basically, they proved that for this third term on the asymptotics, only the relations with the points on a neighborhood matter. So if I'm working with the sphere, I don't have to worry about the points that are on the other side of the sphere. They came to play a role on the first term and on the second term. And I only have to worry about looking at my point, a little neighborhood surrounding my point, and looking at the relations with the points on this neighborhood. And so, if we don't longer care for the total sphere, then I can project this little neighborhood into a plane, into the tangent plane. And then I can translate my problem of minimization here in the sphere to the tangent plane. And I have another problem of minimization with another, not the logarithmic energy on the plane, but another kind of energy, right? And then they propose some candidates for me, the minimizers of the problem of the plane. And these candidates, given back to the sphere, give us a conjecture for the value of this little c constant. And the value that was conjectured in the article is written here. This 2 log of 2 a half blah, 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 approximately minus 0.055. Right. So that was a big step and was done using basically the techniques that were proposed in a previous paper by Serfati and Sandier. All right. They were not the only ones on proposing this conjecture, because in a previous paper by Braucher, Harding, and Saab, one of those papers where they were giving bounds for the previous constant, they proposed exactly the same candidate here for B the third term. This constant times big N. All right, so we have these two conjectures motivated by two different techniques that lead us to think that this is the correct constant for the third term. And just some months ago, on the archive, it appears this paper by Tetrache and Serfati, where they relate this conjecture on the value of the constant on the log term, sorry, on the n term, with yet another well-known conjecture that is the Kohn-Kumar conjecture. So maybe some of you know this conjecture. If it's not the case, I'm going to show you here, just to have a flavor of what kind of conjecture it is. So this Kohn-Kumar conjecture was appeared on a paper on 2007, and I'm going to read it as it is written on the paper, and then I will explain some notation that I didn't want to include here, not to make it more difficult than what it's supposed to be. Okay, so in dimension 2, 8, and 24, the lattice lambda 0, that I will explain which one it is universally minimizing in the sense that it minimizes EP among all possible point configurations of density 1 for all p's that are completely monotone functions on the square distance. What does it mean? It means that here we have EP is some energy that is depending on a function P that again is depending on the distance between every pair of points. Right. So, and I guess that's all we have to worry in this talk. We have here some energy that is depending on a monotone function P that is dependent again only on the distance in between every pair of points of my set. And here, the lattice A0 in dimension 2 is just the triangular lattice. The lattice in dimension 8 is the EH lattice, also called Gosset lattice. And in dimension 24, we have the Leech lattice. So what they were conjecturing is in dimension 2, the triangular lattice is the minimizing, give us the minimizing configuration for a big set of potentials. In dimension 8, the EH or Gosset lattice is giving us the minimizer for another well set of potentials. And in dimension 24, the same with the Leech lattice. All right, so that was a conjecture open since 2007. And last year, it was proved for the case 8 and 24. So if we have 8, dimension 8, yes, the EH lattice is the minimizer. If we are in dimension 24, then yes, the Leech lattice is the minimizer. And dimension 2 is still open. And dimension 2 for this conjecture is actually equivalent to the previous conjecture that we saw here, that the constant for this expression of the minimal logarithmic energy is exactly this. And this is not trivial to prove, and this is the main topic of this article by Tetrache and Serfati from last year. They proved that the constant here to be exactly this number is equivalent to this triangular lattice to be the minimizer of a big set of potentials on dimension 2, right? Maybe I should mention here, this is the result of a work by Kohn, Kumar, Miller, Radchenko, and Biazowska. And this work follows these big works of the minimal Kissing number of dimension 8, first done by Biazowska, and then this extension, dimension 24, done together with some people of this, that are also co-authors of this theorem. And still, many other papers are coming from this big issue. All right, so we have our first relation of the day. Minimizers of logarithmic energy are related to this conjecture for lattices on dimension 2. All right, let's go back to Ismail's seventh problem. Now that we know what is known about the minimal value of the logarithmic energy, namely, we know the expansion up to an n term. N is the number of points, and we know no more. So you can see for the for what was asked here, that we are really far for obtaining a solution, because here we need a set of points that is close enough to the minimizers on the log n, up to a log n asymptotic expansion, and we don't know even where the log n comes on this for the value of this minimal logarithmic energy. So yeah, not big hopes for the moment. We are far away from this problem, but I'd like to tell you a little bit about the motivation for Ismail to put this problem into this famous list of problems. All right, not only why this problem should be there, but also why this condition. Why do we need to know exactly up to this log n term? Okay, and for this, first I have to give you some more notation. We are still, well, with omega n is a set of points on the sphere of dimension 2. But whenever we have a set of points here in the sphere of dimension 2, we can project them into the complex plane using the stereographic projection. Right? For those of you that don't remember that, we take a point in a sphere, then we draw the line passing through the North Pole and my point, and this line is cutting the complex plane on just one point. And this is the image of my projection. And this projection establishes a bijection in between the sphere without the North Pole and the complex plane. And if we add the North Pole, then we are compactifying the complex plane and we obtain a model for the complex projective space. But for the model, that's what we have. We have a bijection in between points on the sphere without the North Pole and then the complex point. All right, whenever I have a set of n complex points, then I can define a unique polynomial that is monic and that has those points as roots, if I'm counting on some multiplicity, right? So this is what is written here. First, I take a set of spherical points. I can project them into the complex plane using the stereographic projection, and I obtain a set of points that I call set I, that are just complex points. And then for those set I have a unique polynomial that is monic and that has those points as roots that it can be written, can be expressed in this way. So what I'm doing here is actually a bijection in between the sphere without the North Pole and the monic polynomials of n different roots of degree n. Yes, roots can be the same. If I here twice the same points, then I have here twice the same points, and I have a root with multiplicity 2. It's not an issue. All right, but I have this bijection. And I'm going to use this notation from now on. Omega n, set of points on the sphere, set I, my points on the complex plane, and Pn is the polynomial obtained by this process that I just described. All right, so using this, we can talk about the condition number of a polynomial. The condition number of a polynomial is just a number that measures how much the root of a polynomial move when I move a little bit the coefficients. It's a notion of numerical analysis and tells us about the stability of polynomials. So you can take your favorite polynomial on one variable, then you change one coefficient by epsilon, and then you compute the roots of this new polynomial and compare them with the previous one. Okay. For some polynomials, the roots are going to change a lot if we just change a little bit one of the coefficients. And for other polynomials, even if we change quite a bit every coefficient, the roots are going to be more or less the same. This is something that can be measured and is measured here by this concept, the condition number, that is defined as follows. I call mu of f, the polynomial, at its root z, the condition number of f at the root z to this quantity here. I don't want to go deeper in this notion. I just want you to have an idea of what is measured. If the condition number is close to 1, then the roots doesn't change so much. And if the condition number is big, then the roots are moving a lot if I change a little bit the coefficients. Okay, and the point is that we can compute it explicitly with a formula, and the formula that is usually used is this one. Then we have another formulas with some normalization factors. And then whenever I have the condition number of a polynomial in one root, I can just compute it for every root, and I call the condition number of a polynomial the maximal of the condition numbers of the polynomial in every root.
Okay, sorry,
Yeah.
what is this norm here?
The norm of f. This is usually
Yes.
for this definition, this is the Bombieri-Weil norm. Do you know what it is?
Vague. I think we would all appreciate a reminder.
Okay, the Bombieri-Weil norm of a polynomial, you just think of the L2 norm of a polynomial, right? The L2 norm, taking the coefficients, is the square root of the sum of the modulus of the coefficients squared, right? This is the L2 norm of a polynomial, the square root of the sum of the modulus of the coefficients squared. And now the Bombieri-Weil norm is exactly this, but not every coefficient is having the same weight 1. We are introducing some combinatorial coefficients, namely the combinatorial number is of the total degree of the polynomial over the position of the different coefficients. But you can think of it as an L2 norm with weights that are not all equal.
Thank you.
Is that okay?
Thanks. Yep.
Oh, right. Of course, this can be also defined for another norms, but then we have to change a little bit the definition. And I want to use here the Bombieri-Weil norm because this is the one Smail was thinking about when coming to this logarithmic energy problem. That is where we are going through, even though now it seems we are far. Okay, but we are not so far. In 1993, Mike Schut and Steve Smail proposed the following problem. Give explicitly a sequence of polynomials where I'm indexing the polynomials on the degree such that their condition number is small enough. And for saying the condition number is small enough, they are saying, okay, it's growing as a polynomial, right? It's bounded, the growth is bound by some polynomials. Okay, there is a motivation for considering that this is small enough, right? But the point is that, of course, there are a lot of people interested in working with polynomials in which if I change a little bit the coefficients, the roots are not changing so much. Or at least I can control how much they are changing, right? Of course, especially looking towards computational applications. So this is the problem they propose. Just give us a sequence of polynomials for which if we move a little bit the coefficients, the roots are not changing so much. And it seems to be a not so difficult problem. I mean, those things can be managed. We can do a lot of experiments with the computer to see how the condition number is growing and blah, blah, blah. But it was an open problem for many years, right? For example, if you take here Pn, let Pn be the roots of unity, the n roots of unity, then we can define a sequence of polynomials as given by the roots of unity. And then this condition number is growing exponentially on the degree. Not as a polynomial, but an exponential function. And you try to play with this with many well-known families of polynomials, and all of them seems to be growing really, really fast. So that was the problem proposing this article. But of course, the article didn't contain only an open problem, but a big theorem, because in there, Ujué and Smale were able to prove that elliptic Fekete polynomials are well conditioned in this sense. And elliptic Fekete polynomials are just the polynomials that we obtain if we take a set of minimizers of the logarithmic energy on the sphere. We project them into the complex plane, and we take those points as roots of my polynomials. Then those are well conditioned. And not only, this is working not only with minimizers of the logarithmic energy, but with points whose energy is this close enough to the minimal logarithmic energy. So mainly what the proof is, okay, if we have a set of points whose logarithmic energy satisfy this inequality here, then we just project them, take the complex points, take them as roots, compute the polynomials, and we are done. Then those polynomials are going to be well conditioned. So the motivation for this Smale's seventh problem doesn't come from potential theory directly, but for this problem of stability of polynomials, right? But it turned out this year, together with Carlos Beltrán, Jordi Marzo, and Joaquim Ortega Cerdán, we were able to solve this problem of Ujué and Smale. We were able to find a sequence, an explicit sequence of polynomials with a small condition number, and still the other problem, Smale's seventh problem, is completely open, right? So it turns out that the problem that was thought to be difficult is not as difficult as the previous one. So this is, you don't have to read this thing here. It was just to make you believe that this is highly explicit, right? We were able to compute such polynomials, and the condition number of those polynomials is really small. Actually, here is bounded by n, and a equals a half. So not even polynomial, but it's sublinear growth. Okay, so we were able to solve this problem, but the previous one remains open. And with the techniques that we use for this, cannot be applied for solving Smale's seventh problem for the moment. We need more. All right, so let's go back to this relation I just mentioned. In 1993, Mike Ujué and Steve Smale proved that elliptic Fekete polynomials are well conditioned. Namely, if the logarithmic energy of my set of points is bounded by the minimal logarithmic energy plus some extra term depending on log of n, then the condition number of the related family of polynomials is bounded by this thing here that has some polynomial growth, right? I don't know how many, I don't know if I'm saying that too much or too little, but this omega and this Pn are related by this stereographical projection, right? Sphere, projection, take my polynomial. So there is a bijection in between my set of points and my polynomials. All right, so namely, if the logarithmic energy is small enough, then the condition number is small enough. And that's a relation. And the other relation was given last year, and it's saying exactly the reverse result. If the condition number of any sequence of polynomials that I can think about with complex coefficients and one variable is bounded by this, then the logarithmic energy of the points obtained by computing the roots of my polynomials, projecting them back to the sphere through the stereographical projection of the inverse, is bounded by, and here we have the minimal logarithmic energy plus some extra n term. Okay. So now we have a complete relation. Well-conditioned polynomials give place to points with a small logarithmic energy, and points with a small logarithmic energy produce well-conditioned polynomials. It's completely closed. And now that we have this relation, this second relation of the logarithmic energy, it appears naturally a third one that apparently has nothing to do. And it's given by this formula. This is a formula that first appeared on an article of Armentrano, Beltran, and Sharp in 2011. And it's really easy to prove. I mean, it's not even proof of on the article. You can write it down, and then you will see how terms cancel and everything fits. And this formula is telling us that the logarithmic energy of a set of endpoints is, and here we have the sum of the logarithm of the condition number of the polynomials and at some roots. Okay, so this term is involving this condition number thing of numerical analysis. And then we have here a third term, n times the logarithm. And here we have some quotient relating the modulus of the roots of the polynomial and the norm of the polynomial. Here again, this norm is the Bombieri-Weil norm that we were using before for defining the condition number. And here we have some extra terms, but if you look carefully to these terms, not any xi appears, not any zi appears. Those terms don't depend on the configuration of the points, only on the number of the points, n, right? So if I'm worrying about how these quantities, the logarithmic energy, change with different distribution of points, I can forget about these terms. They are not adding anything, but here they are included. We have been talking about this guy and this guy for a while, so let's focus on what is this third thing. And it turns out that this quotient here, if we write this PM polynomial that we know is monic, like this, the product of the monomials, then it turns out that this thing here is also the norm of any of the monomials using this Bombieri-Weil norm, that in this case is equal to the L2 norm for degree 1. So this quantity here is just a comparison in between the product of the norms of some monomials and the norm of the product of the monomials. This is what I have, a quotient involving these two things. And working with the previous formula and with the known results for the logarithmic energy for the condition number, we were able to bound this quotient by the following way. So the product of the norm of the monomials is bounded by this term times the norm of the product of the monomials, and this term is growing as an exponential with an exponential factor, right? But this result, this kind of inequality, is maybe familiar to some of you because it's related to a very famous inequality on number theory, namely the Bombieri's inequality. Bombieri's inequality is given a bound for the comparison in between the product of the norms of polynomials and the norm of the product of polynomials. This is a classical inequality stated in 1990 by Bosami, Bombieri, Enflo, and Montgomery. And we know that for two polynomials, this result is sharp. So this is the best constant that we can have here. But for more than 2 polynomials, this result is no longer sharp. And if we take here P1, P2, n polynomials, and every single one of these polynomials to be a monomial, then we obtain this corollary, let's call it a corollary of Bombier's inequality. We just have to prove by induction that we can have such an inequality for 3 polynomials and for 4, for 5, forever. And we have this. And this was the best result that was known until date for comparison of the product of the norms of some monomials and the norm of the product of the monomials. Okay, and here you see it's growing as a potential, has a potential growth. This is like n to the power n. And so this new result here gives us the correct order of growing of such an inequality. So Bombier inequality is sharp, but if we were generalizing it for more than 2 polynomials, that was no sharp, and the true order of growth is this one. And this is not obtained using any of the techniques that Bombieri and Enflo are using for this kind of problems in arithmetic number theory, but using this relation with the condition number of polynomials and the logarithmic energy. I didn't mention that, but this inequality is sharp. So this is the correct order of growth. All right, so we have this new relation here with this Bombier inequality. And now we have a conjecture. I told you that this is sharp, this new inequality is sharp, and I should say, yeah, it's sharp on the order of growth, but we can have here a better constant than 1. So for some n's, for example, if we take n equals 2 or n equals 3, this can be computed explicitly, and here this constant is around 0.9 and not 1. Okay, so let's call Kn the minimal constant, the minimal number, making this inequality sharp, making this inequality still true, right? And this can be, of course, different for every n. Right. Then the conjecture is, all right, this is essentially a constant. And this is essentially a constant in the following way. This is essentially a constant a, and then we have some little term, little o of 1. And as n goes to infinity, this is not going to play an important role here, right? And actually, this new conjecture about the about the constant here, the new Bombieri inequality, is related again to this old conjecture by Kohn and Kumar, and this old conjecture about the value of the constant that goes in this asymptotic expansion of the minimal logarithmic energy. Yeah, so basically, if we have this here, then we can also, this conjecture is equivalent to the previous one. I want to mention something here. This is only numerical experiments, so there is no an analytic statement of that. But if we try to minimize this logarithmic energy, then this thing got minimized, and this thing got maximized. And if we try to minimize the condition number, then this thing got minimized. We know this relation also analytically due to the previous results I've shown you. But this thing here got maximized again, right? So the behavior is pretty clear, or at least numerically. When we are trying to minimize this gets minimized, this gets maximized. And so this is why this conjecture here will imply another conjecture for the minimal logarithmic energy. All right. How much time do I have, Ryan?
So I would say that, so we started about 3 minutes late. Right about now, we've actually hit the 50-minute mark.
Exactly, that's what I was thinking. So perfect, then I won't say anything about the minimizers of the logarithmic energy, and I will end up here. Thank you.
Thank you very much, Ujué. So please be aware that this talk is still recorded. So are there any questions? Please, Hans.
we're going to do a round of recorded questions, and then at some point I will say that the recording's no longer on, and then if there are questions beyond that, those can also occur. I think I saw Hans.
Yeah, I wasn't trying to ask a question. I was trying to hit the clap button, and I found it.
I see. Yes, there is an applause button. Please think of it at the end. Anyways, are there any questions right now?
How do you raise the hand, Peter Dragnev? I have a question.
How do you raise the hand? Okay.
Raise the hand.
Oh, you can just say your questions aloud. You don't need to raise your hand.
So what's the connection between the constant A and the original constant for the packing in R2?
Yeah.
The Kahn-Kumar
You
conjecture.
mean exactly this Kahn-Kumar conjecture? I cannot give a terrific answer. So if you want to know exactly the connection in between this constant on the minimal logarithmic energy and this D equals 2 case, there is this nice article of 20 pages that is going through this, making this. I mean, an idea is that it's also related to the proof of Betterman and Sandier, right? This projection locally on tangent planes, and then looking for the triangular lattice on the tangent plane. That is way more involved than that.
So my question is then, is your constant A conjecture right up to these?
How is this? Yeah, because of basically, because of this formula, basically. So you can prove that if you have here a really big number, this is going to be really small. You cannot prove all the, I was not able to prove all the equivalencies, but yes, to prove that if this is small, this is going to be very big. Yeah, and then you can go through the different terms of the asymptotic expansion, and the important ones again are the, here in this case, the roots of the polynomials that are too close to each other. And these are those are the ones giving us the best constant here. Those are also the ones involved on this constant for the n term here. So it's not completely proof, but it's only on a way. If this is minimal, then we are having here a constant. So if we prove, yeah, the other way around is the nice proof.
Thank you.
Welcome.
Any more questions?
I had a question about also about the relationship between the Kahn-Kumar conjecture and the things related to the Smell problem. So that relationship that you're talking about, would it only be for the Smell problem in dimensions 2, 8, and 24, or does it somehow relate to other dimensions as well?
Okay, if I understood correctly, you're asking if there is those are equivalent conjecture in those dimensions, 2, 8, and 24, and the expansion of the logarithmic energy.
Yes.
In any dimension, right? No, not even in 8 and 24, up to my knowledge. This is not true. The only relation that was proved to be true, that if this conjecture is true, then this one is true, is for dimension 2. So this is only, of course, you can define the whole theory of the logarithmic energy of sphere of arbitrary dimension, but for this we know way less than in this case here for the asymptotic expansion. We are far from this term, and we have no idea of the relation with these lattices in dimension 8 and 24.
Okay, thank you.
Okay.
Yes, any more questions?
I have another question. So could you go back to the slide where the calculation is, where it said there's no proof for it? So this formula with the logarithmic energy.
Sure. This one?
This one. And did I got it correctly? For the second term, you prove an upper bound, right?
Yeah.
And if you put in your upper bound, this is not of the correct behavior, right? So it's bad then?
It is of the correct behavior.
It is of correct behavior then. Okay, then
Yeah,
I got
exactly.
something wrong. I thought there was an additional n then there. Okay.
No, it is of the correct behavior because I am looking up to have here an upper bound. There is also a lower bound, but with a different constant. But the order of growth is the good one. And this is why I obtained directly this.
But is it true that the maximizer of the second term, so in the logarithm, gives also a minimizer for the logarithmic energy, or is there nothing in this direction?
Yeah. You mean for the second term here, the logarithm of the condition number? Minimizers?
No, the other one.
The other
one
one,
afterwards.
no, it's not. I mean, numerical analysis. Yeah, numerical results. Anything analytic.
Thanks.
Any more questions?
Yeah, I have a question, Arno Keilers. I'd like to ask about these well-conditioned polynomials, right, that you constructed with optimal condition number. You showed some impressive formulas. Is there anything you can say about the construction?
Sure. Yeah, I can tell you how we did it. Actually, we were, of course, looking for minimizers of the logarithmic energy and not for well-conditioned polynomials. So what we did was build a net on the sphere of dimension 2 of well-distributed points. Basically, by taking some parallels on the sphere and then taking some roots of unity in every parallel. And this way, we could control the distance in between every pair of points on an easy way. Those were the candidates for minimizers of the logarithmic energy, but we could prove anything, but then we could project them. And we could work with these complex points. And that's what we use to build such polynomials. And if you look at these formulas here, they're basically products of roots of unity, because we have just concentric circles on the complex plane and taking some roots of unity in every circle. So those are the polynomials.
Okay, thank you.
Welcome.
Thank you. Are there more questions?
There are some
please
questions in the chat, it seems.
Oh,
Okay.
can I read it?
Then-
Wait a second. Well, actually, I can stop sharing this. Yeah, and now I can see.
Or otherwise, I would suggest, Ryan, we just stop the recording and people can ask it directly.
Yeah, so I'm going to stop the recording here. So if anybody was worried for that kind of reason, then that will no longer be happening.